Hello, my name is, and today I'll be giving you a brief presentation on my SHINE research project this summer. This summer, I researched policy optimization for multi-agent pathfinding. So without further ado, let's begin. First, a brief introduction. I'm currently a rising senior at Manuart Senior High School, and I have a strong interest in computer science and artificial intelligence. Recently, interest in MapF has grown in the AI research community because of its real-world applications, such as warehouse management and aircraft management. However, current mapper frameworks either give up optimization over speed or speed over optimization. There's always that trade-off. So PhD mentor Eric Ewing and I helped develop a faster mapper planner using reinforcement learning and a deep neural network. More on that later. This is important because improvements in mapper frameworks can help with its real-world applications and make it a lot more efficient and a lot safer for the people involved. So our methods. So first we started with identifying our environment's observations that we would put in as inputs into our neural network. Here we have a diagram of our neural network. We have the input, we have two convolutional layers, put that into a flattened layer, making it a one-dimensional array, put that into a fully connected, which is our last layer. We have that actor critic layer. And the reason we have that is because we use the advantage actor critic A2C algorithm to train our neural network. And the outputs of our neural network that we're trying to get are the actions that the agents should take. For example, you have stay, up, down, left, or right. We also have a value output that tells us how good and the actual value of an action that the agent is about to take. So once we trained our neural network using A2C, we ran experiments where we calculated the success rate or the solution length of our MapF planner. So our results. First, we have the graph of success rate per increase in number of agents. And the key takeaway there is that as you increase the number of agents, the environment becomes progressively harder to solve because MapF is an NP-hard problem, meaning you can't arrive at an optimal solution in polynomial time. Next, we have solution length per increase in obstacles. And the key takeaway there is that solution length increases because more obstacles make solving the environment more difficult. And as you increase the obstacle rate, you also get a higher probability of getting into what's called a deadlock, which is a situation where the agent can't solve the environment because it's probably blocked by two obstacles or its goal is blocked. And obviously that would be impossible to solve. So that's what the shaded regions mean in this graph in the middle. Then we have solution length per increase in size of the environment. And the key takeaway there is that the solution length increases because there are more steps for agents to take, which makes sense because if you have an environment and you increase it, it'll take you more steps to get where you need to go. So our conclusion. We concluded our research project with a faster MapF framework, but we can still build upon what we built by seeking better optimization instead of speed, or comparing and contrasting different neural network architectures to just better that framework that we built. I personally will build upon the research at the college I attend next fall, and I'll be looking at recent publications of new MapF planners and try creating my own MapF planner as well, using what's available at the college. And before I conclude, I just want to give a special thanks to Professor Noor Ayanyan, who accepted me into the ACT lab. Special thanks to my PhD mentor, Eric Ewing, who taught me all this content in a matter of 7 weeks. And it's part of the reason why I now want to pursue research in college. My lab partner, Verinda Bansal, who was there with me along the journey. Center mentor, Ashley Perez, for making the SHINE experience a lot more memorable. And last but not least, Dr. Katie Mills, for reminding me that I didn't have to choose between CS or politics, and then I could just go and explore the fields that really matter a lot to me. And that concludes my presentation. I hope to speak to you once again, maybe in the future when I create my own MapF planner. Thank you.